The X-59 is not just a demonstration of engineering skill. It is a real-world experiment designed to gather data that no computer simulation can fully predict. In the world of aerodynamics, even the most advanced software can only approximate how air behaves at supersonic speeds. Small imperfections in the surface of the aircraft, changes in temperature, humidity, and atmospheric pressure, all of these variables affect how sound travels through the sky. That is why the X-59's flight program is so critical. It will provide the first direct evidence of how a quiet supersonic aircraft performs in natural conditions, outside the confines of a laboratory or wind tunnel. Each test flight of the X-59 will be carefully monitored by a network of ground sensors, microphones, and specialized instruments. These devices will measure the strength, timing, and character of the sound waves created as the aircraft passes overhead. At the same time, high-speed cameras and radar will track its position, velocity, and altitude. By combining these data sets, NASA engineers can map exactly how the aircraft's design affects the pressure waves that reach the ground. Every second of flight will yield valuable data that will be studied and compared with the predictions made during the design phase. But measuring sound is only part of the story. The X-59 program also includes the human element. NASA's researchers plan to fly the aircraft over several test communities in the United States, chosen for their variety of landscapes and populations. In these areas, residents will be invited to share their experiences, whether they heard the aircraft, how loud it seemed, and how they felt about it. This feedback is crucial. If most people describe the sound as mild or barely noticeable, it will support NASA's goal of proving that quiet supersonic travel can be compatible with everyday life on the ground. Inside NASA, multiple teams are collaborating on this effort. The Armstrong Flight Research Center in California will handle much of the flight testing, while the Langley Research Center in Virginia will analyze the acoustic data and community responses. The Glenn Research Center in Ohio contributes expertise on propulsion and aerodynamics, and the Ames Research Center provides computational modeling and simulation support. It is a true multi-center effort, combining decades of experience from across NASA's aeronautics network. The aircraft itself represents a combination of technologies drawn from many earlier programs. For example, the materials used in the X-59 structure are based on composite construction techniques developed for NASA's previous experimental aircraft. These lightweight yet strong materials are essential for maintaining the aircraft's shape at high speeds while minimizing fuel consumption. The flight control software borrows from systems used in both military and civilian jets but has been modified for the unique aerodynamics of the X-59. The aircraft's unique geometry is both its greatest advantage and its biggest challenge. The extremely long nose and thin fuselage provide the desired acoustic profile, but they also create aerodynamic effects that must be carefully managed. Stability, center of gravity, and lift distribution are all finely balanced. The digital flight control system automatically compensates for small shifts in these forces, ensuring the pilot can focus on navigation and mission tasks without constant manual adjustments. Inside the cockpit, the technology is unlike any other experimental aircraft ever built. The external vision system replaces the need for a front windshield entirely. Two high-resolution cameras mounted on the aircraft's nose feed continuous images to large monitors inside. These cameras are equipped with sensors that adjust automatically for brightness, contrast, and glare, ensuring visibility even during direct sunlight or low-light conditions. Additional infrared cameras assist with landings and night operations. Together, these systems provide the pilot with a level of awareness that would be impossible through a traditional cockpit window, especially given the X-59's elongated design. Beyond the cameras, the aircraft's avionics are deeply integrated with its control surfaces. Tiny adjustments to the flaps, rudder, and stabilizers are made automatically in real time to reduce turbulence and vibration. Sensors throughout the aircraft monitor temperature, pressure, and stress levels. Every piece of data is transmitted back to NASA's ground control centers, where engineers can observe and analyze the flight in progress. Safety has been a top priority from the very beginning of the project. Supersonic flight involves extreme forces, and even small design errors can have major consequences. Before a single flight, the X-59 will undergo hundreds of hours of ground testing. The landing gear, fuel systems, and control actuators will all be tested under simulated flight loads. The first time the aircraft takes off, it will do so in stages, beginning with low-speed taxi tests, then subsonic flights, and only later reaching full supersonic speeds once all systems have been verified. The goal of these tests is to ensure that the aircraft performs exactly as intended, and that the noise it generates is within predicted limits. If successful, the results will validate decades of research and open a new chapter in aviation. The long-term vision is to hand this data to the commercial aviation industry, allowing private companies to design and build quiet, supersonic airliners for passengers. The impact of such a breakthrough would be enormous. Imagine traveling from Los Angeles to New York in just over 2 hours, or from London to Tokyo in under 6. Routes that currently take an entire day could be completed in a single morning. Business travel, global logistics, and even tourism would be transformed. Entire industries could emerge around high-speed international transport, and the way people think about distance could change forever. However, speed alone is not the only concern. Modern aviation faces growing pressure to become more sustainable, and NASA is aware of that challenge. The X-59 is not intended to be an energy-efficient commercial aircraft, but it does serve as a test bed for technologies that could eventually make supersonic travel cleaner and more environmentally friendly. Engineers are studying how the aircraft's aerodynamic efficiency can reduce drag and fuel use. Future generations of quiet supersonic jets might incorporate alternative fuels or hybrid propulsion systems to further cut emissions. The data from the X-59 program will also help refine computer models that predict environmental effects. By understanding exactly how supersonic sound waves travel through the atmosphere, researchers can develop better ways to minimize their impact on both people and wildlife. Noise pollution is a major factor in the approval process for new aircraft, and NASA's findings could reshape how future planes are certified for flight over land. While the X-59 is a symbol of technological progress, it is also a reminder of how international cooperation shapes the future of aviation. Supersonic flight is not limited to one country. It is a global concern. Organizations in Europe, Japan, and other parts of the world are watching NASA's results closely. The International Civil Aviation Organization, or ICAO, will use the data from NASA's community response studies to help define new international standards for acceptable noise levels. If those standards are approved, they will open the door for a new era of global supersonic travel. At the same time, private aerospace companies are already taking interest. Several startups and established manufacturers are exploring commercial supersonic jet concepts. But before they can take off, they need proven evidence that quiet flight is possible and legal. The X-59 provides exactly that foundation. NASA's work could therefore become the catalyst that enables private companies to design passenger jets that are fast, quiet, and safe for overland routes. Technologically, the success of the X-59 would validate a number of scientific principles that could apply far beyond supersonic travel. The same shockwave management techniques might be used in spacecraft re-entry systems, drones, and even high-speed ground vehicles. The study of how air pressure waves can be controlled and shaped opens new possibilities in fields as diverse as acoustics, energy transfer, and advanced propulsion. One of the most fascinating aspects of the X-59's design is how it redefines what an aircraft should look like. Traditional airplanes are shaped to maximize lift and minimize drag, but the X-59 introduces a new priority: sound control. This new design philosophy could influence the way engineers think about vehicles of all kinds, shifting focus from raw speed or efficiency to the total environmental footprint of a machine. The X-59 shows that engineering innovation can balance performance with responsibility. The aircraft's digital systems also represent a leap forward. Modern jets rely heavily on computer-assisted controls, but the X-59 takes this a step further. The integration of real-time data analysis allows the aircraft to adapt to changing atmospheric conditions mid-flight. As sensors detect slight variations in air density or temperature, the flight control algorithms adjust the aircraft's angle of attack and control surface positions automatically. This not only enhances safety, but also ensures that the aircraft maintains the optimal, low-noise profile throughout its flight. The long-term influence of the X-59 will depend not only on its technical success, but also on how society responds to it. Public acceptance is essential for any new technology, and NASA's approach, flying over real communities and collecting feedback, shows a recognition of that fact. This transparency builds trust and ensures that